At a distance of 642 light-years, a star 700 times larger than our Sun is preparing for the most perfect death in human history. You might think space is calm and predictable, yet the universe around us is experiencing events far beyond our imagination. Tonight, we will set out on an exploration toward microquasars that fire particle beams at impossible speeds, passing through plasma highways carved by ancient explosions, and moving past rogue black holes hunting through our galaxy. We will witness a hidden companion star that delays cosmic destruction, explore tunnels that connect distant worlds, and learn why our night sky is standing on the edge of a transformation. If you're subscribed, we can begin. When scientists finally detected the ghost following Betelgeuse, they couldn't believe what they were seeing on their screens. For decades, astronomers watched this red supergiant dim and brighten in mysterious cycles. They believed the star was dying, with carbon in its core burning like a cosmic time bomb. But the truth shocked everyone who thought they understood stellar death. We introduce you to Betelgeuse's companion, a blue-white companion star no one expected. This stellar partner orbits Betelgeuse once every 2,100 days and behaves like a cosmic snowplow moving through clouds of dust. Think of a speedboat cutting a wake across water. As this companion passes through the material constantly ejected into space by Betelgeuse, it creates the brightness changes we observe from Earth. The discovery was made using the Gemini North telescope with a specialized speckle imaging technique. Scientists found this hidden companion behind Betelgeuse's blinding glare. The blue-white star shines far more faintly than its giant red partner, like trying to spot a candle next to a stadium floodlight. Here comes the shocking part. Betelgeuse was predicted to explode within decades. Astronomers had forecast a near-term supernova based on the brightness cycles they observed. The companion star changes everything. These cycles come not from internal stellar collapse, but from orbital mechanics. Betelgeuse's companion extends the star's lifespan from decades to hundreds of thousands of years. When Betelgeuse finally explodes, the spectacle will be unlike anything in recorded human history. The supernova will shine at a magnitude between -10 and -12. Imagine a star as bright as a half moon, visible in daylight for months. At midnight, you could read a book by the light of the supernova. The explosion will cast shadows on Earth from 400 trillion miles away. Betelgeuse extends to 700 times the radius of our Sun. If you placed this monster where the Sun is, its surface would stretch beyond Jupiter's orbit. Material released by recent surface eruptions equals the combined output of 400 billion solar flares. During the Great Dimming event of 2019-2020, 40% of the star's light was blocked by clouds of ejected dust. Current measurements place Betelgeuse at exactly 642 light-years from Earth. At this distance, the supernova poses no danger. However, neutrino detectors will warn us 10 to 15 seconds before the light reaches our eyes. We will literally watch the future arrive. The discovery of the companion star is rewriting supernova prediction models. Binary systems behave differently from single stars. Mass exchange between stellar partners affects nuclear burning rates. Orbital mechanics influence stellar winds and dust production. What looked like the pains of death were actually movements in a gravitational dance. Betelgeuse's companion teaches us that even the most famous stars still keep secrets. From our perspective, the night sky appears static. Stars seem fixed in constellation patterns passed down for thousands of years. Yet stellar systems reveal themselves in complex ways we barely understand. Multiple star systems dominate the galaxy, while single stars, like our Sun, are the exception. This discovery confronts us with new questions about stellar evolution and supernova timing. How many other giant stars have hidden companions? What other assumptions about stellar death need to be re-examined? Betelgeuse may surprise us again before its final performance. But what is approaching from the depths of space makes Betelgeuse seem like a gentle friend? Within 1.3 million years, an orange giant will dominate Earth's night sky like no star in human memory. When you look toward the constellation Ophiuchus today, you see nothing special. The star hiding there appears so faint that you need a telescope to detect it. And yet, this cosmic sleepwalker will become brighter than all the stars we see today combined. Gliese 710 is creeping toward us at 43,000 miles per hour. This orange dwarf star is currently 63.8 light-years away in the constellation Serpens. With a magnitude of 9.7, it is invisible to the naked eye. Amateur astronomers struggle to find this ordinary K7V class star among thousands of similar faint points. The approaching encounter will completely rewrite Earth's night sky. Gliese 710 will pass within 0.166 light-years of our solar system. That distance is roughly 10 trillion miles, closer than any star has come in millions of years. The orange giant will shine at magnitude -2.7, rivaling Jupiter's brightness and outshining Sirius by a factor of 4. Imagine this cosmic visitor growing brighter each night. Unlike every star you see today, Gliese 710 will appear as a true disk rather than a point of light. The approaching star will become 140,000 times brighter than it is now. You will be able to watch it visibly move across the sky by about 1 arc-minute per year, like the moon sliding past background stars. Gliese 710 will reign as Earth's brightest star for roughly 20,000 years. The encounter transforms far more than brightness records. This stellar visitor will plow through the Oort cloud like a wrecking ball. Gravitational forces will scatter trillions of icy bodies in every direction. The Oort cloud surrounds our solar system like a spherical shell of frozen comets. These ancient remnants from the formation of the solar system orbit at distances of up to 100,000 astronomical units. When Gliese 710 passes through this field of cosmic debris, gravity will hurl countless objects toward the inner planets. Computer models predict that for millions of years following the encounter, about 10 comets per year will stream toward Earth and Mars. The late heavy bombardment that scarred planetary surfaces 4 billion years ago will essentially restart. Impact craters will cover every solid surface from Mercury to the asteroid belt. The orange star is slightly smaller than our Sun, with about 60% of the Sun's mass. A surface temperature of 4,000 Kelvin gives Gliese 710 its characteristic orange color, painting our night sky. Spectroscopic analysis reveals that this star burns hydrogen steadily, without dramatic variability or stellar flares. Advanced civilizations around distant stars likely noticed our Sun approaching their systems millions of years ago. Just as we will observe Gliese 710, they may have watched our yellow star brighten in their skies. Perhaps they prepared for the gravitational disturbance of their own comet clouds. In our galactic neighborhood, the rate of stellar encounters averages 1 close pass every few million years. Previous visitors have repeatedly reshaped the Oort cloud throughout Earth's history. Mass extinction events may be linked to these stellar encounters through increased comet bombardment. Gliese 710 poses no radiation threat due to its stable hydrogen burning. The star does not produce harmful X-rays or gamma radiation, capable of damaging Earth's atmosphere. Instead, solar system dynamics face their primary danger from the gravitational disturbance of long-period comets. Even so, this approaching stellar giant pales beside the architectural wonders carved across our region by ancient explosions. The space between stars hides a secret highway system linking our solar system to distant worlds. You imagine interstellar space as an empty darkness dotted with isolated points of light. That picture is completely wrong. Ancient stellar explosions carved vast tunnels across the galaxy, creating channels of superheated gas stretching for thousands of light years. Scientists using the E-Rosetta X-ray telescope discovered these cosmic highways by accident while mapping background radiation. The space surrounding our solar system glows with million-degree plasma that should have cooled long ago. Instead of random clouds of hot gas, observations revealed organized structures pointing in specific directions. These interstellar tunnels formed from multiple supernova explosions occurring over millions of years. When massive stars explode, they hurl shells of material outward at thousands of miles per second. Imagine throwing a stone into a pond and watching ripples spread across the surface. Stellar explosions work in a similar way, except the ripples are shock waves of superheated plasma expanding through space. Multiple supernovae in the same region create overlapping blast zones. The expanding shells collide and merge, carving channels through the interstellar medium like rivers cutting through a landscape. These cosmic waterways follow paths of least resistance, linking regions where ancient star formation once occurred. The local hot bubble surrounding our solar system spans roughly 300 light-years in diameter. This cavity contains gas heated to temperatures of up to 1.2 million Kelvin, about 100 times hotter than the surface of the Sun. The bubble formed when nearby stars exploded between 10 and 20 million years ago. However, the local hot bubble is not isolated. Tunnel-like extensions connect our cosmic neighborhood to distant stellar regions. The most prominent tunnel stretches toward the constellation Centaurus, potentially providing a direct pathway to the Alpha Centauri system, located just 4 light-years away. These plasma highways offer fascinating implications for interstellar travel. Spacecraft could move through low-density channels instead of pushing through normal interstellar space. The tunnels contain roughly 1/10 the particle density of surrounding regions, reducing drag on hypothetical starships. The tunnel network resembles the cosmic web structure that organizes matter on galactic scales. Just as dark matter filaments connect galaxy clusters, these plasma channels link stellar neighborhoods together. The architecture reveals that supernova explosions follow patterns tied to spiral arm dynamics and the history of star formation. Scientists have discovered similar tunnel systems around other nearby stars. The network may extend along the local galactic arm, potentially forming a transportation grid for advanced civilizations. X-ray observations reveal temperature gradients along the tunnel walls, where hot plasma meets cooler surrounding material. These boundary layers create complex fluid dynamics with regions of turbulence and mixing. Despite ongoing evolution, the tunnels remain stable for millions of years. The discovery shifts our understanding of the interstellar medium from a static void to a dynamic architecture. The space between stars is stirred by ongoing processes driven by stellar evolution. The galaxy operates less like a collection of isolated objects and more like a living organism. Future space missions could use these plasma channels as natural highways between star systems. Reduced particle density would allow higher speeds with less radiation shielding. Interstellar travel becomes far more practical when a cosmic infrastructure is already in place. Yet, the most extraordinary tunnel of all points toward our nearest stellar neighbors, offering possibilities that science fiction has barely dared to imagine. A direct tunnel of superheated gas connects our solar system to Alpha Centauri, creating the first interstellar highway ever discovered. You've always assumed that a 4-light-year journey to our nearest stellar neighbors would require crossing empty space filled with cosmic dust and radiation. The reality is far more astonishing than anyone expected. The Centaurus tunnel extends in an almost straight line from the local hot bubble toward the Alpha Centauri system. This plasma channel maintains remarkably consistent properties across light-year distances, like a cosmic fiber optic cable made of million-degree gas. The tunnel walls display remarkable stability, despite the violent forces that created them. X-ray telescopes reveal the highway structure in exquisite detail. The central channel measures roughly 50 light-years in diameter, wide enough to contain entire solar systems. Temperature readings show the tunnel interior averages about 1.4 million Kelvin, hot enough to instantly strip electrons from atoms. The plasma highway formed from multiple supernova explosions occurring in sequence between our region and Alpha Centauri. Imagine a line of falling dominoes. Each stellar explosion triggered shock waves that carved the tunnel structure deeper. The process required precise timing over millions of years. Alpha Centauri sits at the far end of the tunnel, like a lighthouse marking a cosmic harbor. The triple star system consists of Alpha Centauri A, a sun-like yellow star, Alpha Centauri B, an orange dwarf companion, and the red dwarf Proxima Centauri, which may host potentially habitable planets. The highway reduces travel time for hypothetical spacecraft in unexpected ways. While the tunnel does not shorten the physical distance, its low particle density allows for much higher speeds. Interstellar ramjet concepts could collect plasma directly from the tunnel to use as propulsion fuel. Scientists calculate that spacecraft could reach 10% of the speed of light while traveling through the Centaurus tunnel. With current theoretical technology, travel time drops from 40,000 years using conventional rockets to just 40 years for plasma-propelled ships. Advanced civilizations could cross the highway in decades instead of millennia. The tunnel also provides natural protection from cosmic radiation. Dense plasma walls deflect the high-energy particles that normally bombard spacecraft during interstellar flight. Magnetic fields embedded in the tunnel structure create protective barriers similar to planetary magnetospheres. Temperature measurements reveal fascinating dynamics inside the plasma highway. Hot gas flows toward Alpha Centauri at hundreds of miles per hour, creating a cosmic tailwind that could assist outbound missions. Return journeys would have to fight against this plasma flow, but would still benefit from the reduced particle density. The discovery suggests that similar tunnels connect other nearby star systems. The local galactic arm may contain an entire network of plasma highways left behind by ancient chains of supernovae. Future studies with advanced X-ray telescopes could map this interstellar infrastructure. Proxima Centauri b, the potentially habitable planet orbiting our nearest red dwarf neighbor, becomes far more accessible thanks to the tunnel route. This rocky world receives stellar radiation levels similar to Earth and may host liquid water oceans. The plasma highway transforms Proxima from an impossible destination into a challenging but reachable target. The existence of the tunnel implies that advanced extraterrestrial civilizations may already be aware of these cosmic highways. Any species that develops interstellar travel capabilities would discover plasma channels through X-ray astronomy. They may already be using the tunnel network. Communication along the Centaurus tunnel could also benefit from plasma wave propagation. Radio signals can travel faster through ionized environments than through normal space. The tunnel could serve as a natural waveguide for interstellar messaging. Yet, the plasma highway represents only a single thread within a vast cosmic infrastructure network that dwarfs anything humans have ever imagined. Rivers of plasma, hotter than stellar cores, flow between star systems and create a galactic transportation network spanning thousands of light years. You imagine space as cold and empty, a vacuum that spacecraft must struggle through. The truth reveals that space is a turbulent ocean of superheated gas organized into vast currents that dwarf any terrestrial river system. These cosmic highways carry temperatures reaching 2 million Kelvin, 20 times hotter than the surface of the sun. Plasma flows move at hundreds of miles per hour and generate stellar winds capable of powering entire civilizations. Magnetic fields embedded within the gas streams generate forces equivalent to billions of nuclear power plants. The highway system emerged from some of the most violent events in galactic history. Supernova explosions pump enormous amounts of energy into the interstellar medium and create shock waves that propagate for millions of years. These shock waves heat surrounding gas to extreme temperatures and set it in motion along predictable paths. Think of cosmic highways as celestial arteries carrying the lifeblood of star formation across the galaxy. Hot plasma streams transport heavy elements forged in stellar cores to regions where new stars will form. Carbon, oxygen, iron, and other materials required for rocky planets surf between stellar nurseries within these cosmic currents. Scientists are mapping the highway network using X-ray observatories that detect thermal emissions from superheated gas. The plasma glows like neon lights, marking interstellar highways visible from thousands of light years away. Advanced alien civilizations could navigate using these cosmic landmarks, just as ancient sailors once used the stars. The local hot bubble sits at a major highway junction. That explains the complex structure. Multiple plasma flows converge near the solar system before branching off toward different galactic destinations. We live inside a cosmic traffic hub, connecting dozens of stellar neighborhoods. Plasma speeds inside the highway reach 300 kilometers per second, fast enough to cross the entire solar system in just 1 week. Spacecraft could ride these currents like sailing ships using trade winds, reaching interstellar speeds that are impossible with conventional propulsion. The key lies in understanding plasma physics and magnetic field interactions. Highway walls show remarkable organization despite the chaotic forces that created them. Gradients create distinct layers where the hot central plasma meets cooler surrounding material. These boundary regions can generate turbulence and mixing that enrich the interstellar medium with woven stellar materials. Magnetic fields thread through plasma flows like invisible train tracks that guide charged particles along specific paths. These field lines stretch across light years without breaking, creating cosmic infrastructure that could guide spacecraft navigation systems or interstellar communication. The highways also influence galactic weather patterns by transporting energy between active star-forming regions. Hot plasma from stellar nurseries flows toward cooler regions, equalizing temperatures across vast volumes of space. This cosmic climate control affects where and when new stars can form. Recent discoveries revealed that the highway network connects to similar structures in neighboring galaxies. The local galaxy group shows evidence of intergalactic plasma bridges spanning millions of light years. The cosmic highway system may extend across the observable universe. Future space missions could map these plasma highways in detail and reveal optimal routes for interstellar exploration. Just as ancient traders followed river systems to reach distant lands, spacefaring civilizations could use cosmic currents to traverse the galaxy efficiently. The highway system operates continuously, renewed by ongoing stellar explosions and powered by galactic rotation. Unlike human-made infrastructure that requires maintenance, these cosmic highways are self-sustaining and grow stronger over time as more supernovae add energy to the network. Yet, all of these vast plasma rivers flow within an even larger structure that surrounds our entire solar system in ways we are only beginning to understand. We live inside a giant soap bubble made of million-degree gas stretching farther than most people could ever imagine. You might think our solar system is freely floating through empty space between distant stars. The reality is that we exist inside a vast cavity carved by ancient explosions, surrounded by walls of superheated plasma extending 300 light-years in every direction. The local hot bubble formed 10 to 20 million years ago when massive stars in our cosmic neighborhood exploded one after another. These supernova explosions carved out a spherical void in the interstellar medium, much like underground blasts create cave systems. Shock waves pushed dense gas away from our region, leaving behind a hollow space filled with extremely hot, thin plasma. Inside the bubble, the gas density drops to about 1/10 of typical interstellar values. This low-density environment reduces radiation exposure for any spacecraft traveling between nearby stars. The bubble also blocks cosmic rays from distant galactic sources, creating a partially shielded region around our solar system. Temperature measurements reveal that the interior of the bubble averages 1.2 million Kelvin. This sounds incredibly hot, but the gas is so thin that the human body would instantly freeze despite the high temperature. Think of the difference between a campfire and a blast furnace. Both produce heat, but a campfire contains more total thermal energy because it has more fuel. Within the boundaries of the local hot bubble, there are roughly 500 stars, including many of the bright stars visible in Earth's night sky. Sirius, Procyon, Altair, and other familiar stellar names shine from within our cosmic neighborhood. These stars appear prominent because we observe them through the bubble's clear interior rather than through dust-obscured outer regions. Scientists, using the Arosita X-ray telescope, discovered the bubble's asymmetric shape. Instead of forming a perfect sphere, the cavity shows elongated extensions and irregular boundaries. These deformations arise from interactions with other nearby supernova remnants and with the structure of the galaxy's magnetic field. The walls of the bubble are made of compressed gas heated to temperatures exceeding 2 million Kelvin. These boundary regions glow brightly at X-ray wavelengths, creating a cosmic shell visible to space-based telescopes. The wall thickness varies between 10 and 50 light-years, depending on local conditions. Stellar winds from hot stars inside the bubble protect the cavity against gravitational collapse. These winds carry enough energy to prevent surrounding dense gas from flowing back into the cleared region. The bubble remains stable for tens of millions of years before external forces begin to compress it. The solar system sits slightly off-center within the local hot bubble, closer to the boundary in the direction of the constellation Centaurus. This asymmetric position explains why we see more dust and gas clouds in some directions of the sky compared to others. The edge of the bubble appears across our night sky as the visible band of the Milky Way. Recent studies suggest that the bubble continues to expand slowly as additional stellar explosions inject energy into the structure. Young, massive stars within the cavity will eventually explode as supernovae, potentially enlarging the bubble further or creating side cavities connected to the main volume. The discovery of the local hot bubble revolutionized our understanding of the solar system's galactic environment. Rather than traveling through uniform interstellar space, we live in a special region shaped by cosmic violence. This protected zone may have influenced Earth's climate and biological evolution by reducing exposure to harmful radiation. Across the galaxy, advanced extraterrestrial civilizations likely live within similar bubble structures created by local supernova activity. These cosmic refuges provide ideal conditions for long-term planetary evolution and technological development. Life may concentrate inside hot bubbles rather than in the denser, more radiation-rich regions of the galaxy. The ultimate fate of the bubble depends on future stellar explosions and interactions with neighboring supernova remnants. Our cosmic home will evolve and likely merge with adjacent cavities, creating even larger cleared regions within the interstellar medium. But as we drift safely inside this protective cocoon, somewhere else in the galaxy, a stellar bomb is preparing to explode with the power of billions of nuclear weapons. 3,000 light-years away, a white dwarf star is accumulating stolen hydrogen like a cosmic suicide bomber preparing to detonate. When you scan the constellation Corona Borealis tonight, you see nothing unusual among its faint stars. Yet hidden within this celestial crown, an unseen stellar remnant is racing toward a thermonuclear explosion that will suddenly create Earth's newest naked-eye star. T Corona Borealis consists of two stars locked in a deadly orbital dance. The primary white dwarf has a mass comparable to our Sun, but is only Earth-sized, generating surface gravity 300,000 times stronger than that of our planet. Its companion, a bloated red giant star, slowly bleeds material toward the compact monster through gravitational pull. The mass transfer process is like a cosmic vampire feeding on its victim. Hydrogen-rich gas flows from the outer atmosphere of the red giant toward the white dwarf in a spiraling stream called an accretion disk. This disk glows at temperatures of 50,000 Kelvin, where gravitational energy is converted into heat through friction. Material accumulates on the surface of the white dwarf like snow piling up during a snowstorm. But this stellar snow consists of compressed hydrogen gas heated to millions of degrees. The crushing gravity of the white dwarf compresses the accumulated layer until conditions for nuclear fusion develop at the surface. When the hydrogen layer reaches a critical thickness, explosive nuclear burning ignites simultaneously across the entire surface of the white dwarf. This runaway fusion process releases more energy in seconds than our Sun produces in thousands of years. The explosion hurls the accumulated material into space at speeds exceeding 6,000 miles per second. T Coronae Borealis last erupted in 1946, creating a second-magnitude star visible to the naked eye for several days. Astronomers recorded detailed observations as the new star rapidly brightened and then faded over the course of several weeks. The cycle repeats roughly every 80 years as the white dwarf rebuilds its supply of hydrogen fuel. Current observations show that all indicators point to an imminent eruption. The system has been dimming since March 2023, following the same pattern observed before the 1946 outburst. Spectroscopic monitoring reveals increasing mass transfer rates and an expanding accretion disk radius. The upcoming explosion will increase the brightness of T Coronae Borealis by a factor of 1,000, transforming it from an invisible telescopic object into a star of visible magnitude comparable to Polaris. The eruption will be visible worldwide to naked-eye observers, creating a visible star where none existed before. Professional observatories around the world are preparing for intensive monitoring when the eruption occurs. The James Webb Space Telescope, the Hubble Space Telescope, and ground-based facilities are planning coordinated observations across all wavelengths. This event represents the first recurrent nova eruption observable with modern space-based instruments. The nova explosion will eject roughly 1/10,000th of the white dwarf's mass into surrounding space. This material, enriched with carbon, oxygen, and other heavy elements created during the fusion blast, will contribute to the interstellar medium and to future star formation processes. Timing predictions focus on late 2025, with some models suggesting November 10 as the most likely eruption date. However, stellar explosions follow complex physics that make precise prediction impossible. The eruption could occur on any night within the next few years. The recurrent nova phenomenon demonstrates how white dwarf stars can explode repeatedly without destroying themselves. Unlike Type A supernovae, in which the white dwarf is completely destroyed, recurrent novae blow off only the surface layers while leaving the compact core intact for future cycles. T Coronae Borealis belongs to a rare class of only 10 known recurrent novae in the entire galaxy. These systems require delicately balanced conditions in which mass transfer rates match nuclear burning timescales. Too little material produces no eruption, while too much triggers complete destruction. The upcoming eruption offers unprecedented opportunities to study stellar nuclear physics in real time. Modern instruments can observe the eruption's evolution from initial ignition through material ejection and subsequent cooling. These observations will refine models of nuclear burning on stellar surfaces. Even so, this controlled stellar explosion seems gentle when compared to the rogue celestial objects drifting alone through the cosmic wilderness between stars. One night, this year or next, you will witness something no human has seen for nearly 80 years. A completely new star in the constellation Corona Borealis will suddenly come to life, shining brightly enough to be seen without a telescope or binoculars. This stellar birth does not come from the formation of a new sun out of gas and dust, but from an explosive event violent enough to outshine entire galaxies. The new star will appear between the bright stars Arcturus and Vega, creating the distinctive arc pattern ancient astronomers called the Northern Crown. You can find Corona Borealis by looking northeast on summer evenings, where 7 stars form a semicircular crown. The new arrival will join this cosmic jewel as the constellation's second brightest member. When T Coronae Borealis erupts, the light show begins within hours. The invisible 10th magnitude star will brighten rapidly, gaining luminosity faster than any supernova. Within days, it will reach 2nd magnitude, matching the brightness of Polaris. The creation of a visible star will be observable worldwide to the naked eye for about 1 week. Professional astronomers call this phenomenon a recurrent nova, but the name understates the drama involved. The eruption releases 10 billion times more energy than the most powerful nuclear weapons ever built. If you could bottle the energy from just 1 second of the explosion, it would power human civilization for millions of years. As the ejected material expands into space, the eruption creates spectacular visual effects. High-speed cameras will capture the evolution of the blast, revealing glowing shells of gas, expanding at speeds of 6,000 miles per second. These ejecta form complex patterns as they collide with material expelled during previous eruptions. Spectroscopic observations will reveal the chemical signature of the explosion as different elements produce characteristic colors. Hydrogen burns with deep red light. Oxygen glows green and blue, while carbon appears at ultraviolet wavelengths. The nova becomes a cosmic laboratory for studying nuclear physics under extreme conditions. The brightness of the new star will fluctuate dramatically during the first few weeks after the eruption. Initial observations show rapid brightening following irregular variations as the blast wave spreads through surrounding material. Multiple peaks and valleys create a complex light curve. Unlike the behavior of constant stars, amateur astronomers worldwide will contribute valuable observations using simple equipment. Digital cameras and basic telescopes can track the nova's changes in brightness and color evolution. Citizen science projects will coordinate thousands of measurements from observers in different time zones. The eruption will be visible from every continent outside Antarctica during local nighttime hours. Observers in the southern hemisphere will see Corona Borealis low on the northern horizon, while northern observers enjoy the constellation high above their heads. Light pollution in large cities will dim the view, but cannot hide an event this bright. Space-based telescopes will observe wavelengths invisible from Earth's surface. The Hubble Space Telescope will capture ultraviolet light from the hottest regions of the eruption. The James Webb Space Telescope will peer through dust clouds using infrared detectors. X-ray observatories will track the most energetic emissions from the blast. The appearance of the nova will trigger intense media coverage as news organizations report the sudden creation of a star. Social media will explode with amateur photographs and time-lapse videos showing the emergence of the new star. This will be the first major astronomical event of the smartphone era visible without specialized equipment. Educational systems worldwide will use the nova as a teaching opportunity to explain stellar evolution and nuclear physics. Students will be able to observe ongoing astrophysical processes rather than studying static textbook illustrations. The eruption demonstrates cosmic violence on scales that dwarf everyday human experience. The new star will gradually fade over several months as the ejected material expands and cools. Next year, T Coronae Borealis will return to invisibility, leaving only faint nebular remnants detectable with powerful telescopes. The next eruption will occur roughly 80 years later when today's children have grown old. Yet this controlled stellar eruption represents only one type among many forms of destruction that white dwarf stars can unleash. The most common stellar remnants in our galaxy act as cosmic time bombs waiting for the right conditions to explode. White dwarf stars appear as peaceful points of light, slowly cooling over billions of years. The reality is far more explosive. These stellar corpses can trigger nuclear blasts rivaling the most violent events in the universe. White dwarf stars form when sun-like stars exhaust their nuclear fuel and shed their outer layers. The remaining core collapses under its own gravity until electron pressure halts further compression. The result is a stellar remnant compressed into a sphere the size of Earth with the mass of the Sun. The surface gravity on a white dwarf reaches 300,000 times that of Earth. A sugar cube on such a world would weigh as much as a car. This crushing gravitational field creates the conditions necessary for explosive nuclear burning whenever fresh fuel becomes available. Most white dwarfs are found in binary systems with companion stars orbiting them. When the companion expands during its own stellar evolution, material begins flowing toward the white dwarf under gravitational pull. This process turns peaceful stellar remnants into potential superweapons. The transferred material accumulates on the white dwarf's surface in a thin layer that becomes denser over thousands of years. Temperature and pressure gradually increase until nuclear fusion conditions develop. Unlike controlled burning in stellar cores, fusion on white dwarf surfaces proceeds explosively once ignited. Nova eruptions occur when accumulated hydrogen ignites in uncontrolled nuclear reactions. The explosion consumes the entire surface layer within hours, hurling material at thousands of miles per second. The energy release exceeds that of 10 billion nuclear weapons simultaneously detonating on the white dwarf's surface. Some white dwarfs trigger even more catastrophic explosions, called Type 1a supernovae. When accumulated material pushes the white dwarf's mass beyond 1.4 solar masses, the entire star detonates in a thermonuclear explosion visible across billions of light years. Nothing remains except expanding clouds of debris enriched with heavy elements. The galaxy contains roughly 10 billion white dwarf stars, making them the most numerous stellar remnants. About half reside in binary systems capable of mass transfer events. This means there are roughly 5 billion potential nova or supernova progenitors across the Milky Way, waiting for the right triggering conditions. Nova eruptions occur roughly once a year in our galaxy. Most happen too far from Earth or behind clouds of dust to be seen. However, historical records document novae appearing as new stars in familiar constellations, visible to the naked eye for a few weeks before fading. The most famous white dwarf bomb resides in the constellation Cygnus, where the white dwarf WD 1933+229 slowly accumulates helium from its companion star. Astronomers predict that this system will explode as a Type 1a supernova within 100 million years, creating a blast visible in daylight. White dwarf eruptions contribute fundamental heavy elements to galactic chemical evolution. Iron, nickel, chromium, and other metals forged in thermonuclear blasts seed the interstellar medium for future star and planet formation. Every atom heavier than oxygen in your body was likely created in white dwarf explosions. The discovery of white dwarf variability revolutionized our understanding of the final stages of stellar evolution. Rather than simply cooling and fading, these stellar remnants remain active participants in galactic processes through explosive interactions with companion stars. Advanced civilizations orbiting white dwarf systems would face periodic extinction events from nova eruptions. The blast radiation would sterilize planets within a few astronomical units and disrupt atmospheric chemistry across entire solar systems. Survival would require either deep underground shelters or interplanetary evacuation. Future space missions could observe white dwarf systems before, during, and after explosive events. Real-time monitoring would reveal the detailed physics of thermonuclear burning under extreme conditions impossible to reproduce in terrestrial laboratories. While white dwarf eruptions represent the most common stellar violence, the systems that create them display even more dramatic examples of cosmic destruction through gravitational warfare. Two stars locked in orbital combat produce some of the most spectacular explosions known to astronomy. You might imagine binary star systems as peaceful cosmic couples dancing together in space. The reality reveals gravitational warfare that tears stars apart, triggers nuclear blasts, and creates some of the brightest events in the observable universe. Close binary systems experience tidal forces that stretch both stellar partners into egg-shaped objects. Gravitational pull elongates each star toward its companion, creating protrusions pointing at the orbital center. These deformations heat stellar surfaces through internal friction, making binary stars brighter and more active than single stars. When one star evolves faster than its companion, the binary system becomes a cosmic vampire. The more massive star first expands into a red giant, filling a gravitational influence region called the Roche lobe. Material from the bloated giant flows toward the compact companion via the gravitational balance point between the two stars. This mass transfer creates magnificent accretion disks around the receiving star. Imagine a cosmic whirlpool where stolen stellar material spirals inward at incredible speeds. Friction heats the disk until it shines, brighter than many galaxies, producing some of the brightest objects in the universe. The most extreme binary systems contain a black hole or neutron star paired with a normal stellar companion. These high-mass compact objects strip material from their partners with devastating efficiency. Gas falling toward the compact object accelerates to a significant fraction of the speed of light, producing X-ray emission visible across galactic distances.
Cataclysmic variables represent binary systems where a white dwarf siphons hydrogen from its main sequence companion. Accumulated material builds up on the white dwarf's surface until explosive nuclear burning ignites. These nova eruptions can repeat every few decades or centuries, creating recurrent stellar bombs. Some binary systems experience contact phases where the surfaces of both stars actually touch. The two stars share a common atmospheric envelope while their cores remain separate. These contact binaries often merge completely, triggering bright red nova eruptions, temporarily outshining their host galaxies. X-ray binaries produce jets of material moving at nearly the speed of light. These relativistic flows extend light years from the central binary, creating cosmic blowtorches, heating surrounding gas above 1 billion degrees. Although the jets originate from stellar mass objects, they rival quasar emissions. Wolf-Rayet binary systems display the most violent stellar winds known to astronomy. These hot, massive stars lose material at rates millions of times higher than the sun's solar wind. Paired with compact companions, their interactions generate complex shock structures and particle acceleration regions. Symbiotic stars illustrate long-term binary evolution, where a white dwarf slowly accretes material from a red giant companion over millions of years. These systems undergo periodic eruptions as accumulated material reaches critical densities for explosive nuclear burning. The cycle can repeat hundreds of times over the lifetime of the binary. Type 1a supernovae, the thermonuclear explosions that destroy white dwarf stars, occur exclusively in binary systems. The white dwarf must accumulate enough material from its companion to exceed the critical mass limit. These explosions serve as standard candles for measuring cosmic distances and probing dark energy. Gravitational wave observatories detect kilonovae, explosive events from merging neutron star binaries that create heavy elements like gold and platinum. These cosmic collisions occur when two ultra-dense stellar remnants spiral inward and merge, producing catastrophic explosions visible across billions of light years. The galaxy contains millions of interacting binary systems at various evolutionary stages. Each represents a potential future eruption as gravitational forces drive stellar components toward ever more violent interactions. Advanced alien civilizations within binary star systems would experience regular cosmic disasters from the violent interactions of their host stars.
Planetary survival would require either advanced technology to deflect stellar emissions or migration to more stable single-star systems. Yet even all these magnificent binary eruptions appear tame compared to solitary wanderers drifting through interstellar space without any stellar companion. And so, in this vast arena of the universe, we find ourselves in the midst of a cosmic dance spanning billions of years. The approaching supernova of Betelgeuse, the slow approach of Gliese 710, energies flowing along plasma highways, all remind us how dynamic, how alive, how dangerous, yet how magnificent the universe truly is. Every night, when we lift our heads and look at the stars, we do not see merely calm points of light. We witness the cosmic wars, explosions, mergers, and rebirths that have unfolded over millions of years. The night sky may appear static, but the truth is, we are only capturing a single snapshot of the ongoing cosmic drama around us. Stars are being born, dying, and being reborn. Galaxies collide. Black holes dance. And we, in the midst of this magnificent cosmic symphony, on a spiral arm of the Milky Way, on our small blue planet, are the only species striving to comprehend this entire universe. Perhaps the greatest miracle is that, amidst all this cosmic violence and chaos, life can exist, evolve, and begin to unravel the secrets of the cosmos. That truly is astonishing.